sure what he's going to show us, but I think it's very important that we have him here, part of a kind of lecture series we're having with important contributors to contemporary architecture and engineering, because I think you are both an engineer as well as an architect, and I think that's very interesting to me in particular, as some of you have noticed, I'm more and more getting interested in integrating engineering and architecture, having structure an important part to overcome this, let's say, the first infancy of our new style development, where we were talking about volumes, configurations, spatial scenarios, and now we want to go into articulating those through structures. We also want to get into ecological paradigm, bring that in and have the formative aspects, social, structural, ecological, driving the articulation of our artifacts to the high level of detail. So that's why I think it's a great and we are a great admirer also and students of Frei Otto's work, and he is the one who took over from Frei Otto and is now leading the Institute of Lightweight Structures, as well as understand he took over from Jörg Schleich, one of the most famous engineers, excelling in lightweight structure in the sense of lightness and elegance or organic beauty, which we aspire to, we require this close integration with kind of engineering expertise, and that's what we're trying to kind of gear up for. So that's why I think we're very happy to have you here, and also werner Sobek and his team is making already some significant contributions to some of our projects, like one of our major endeavors in Martin, the Life Center, and some other projects. So thank you very much for your time, your precious time, and welcome, werner Sobek.
Thank you very much, Patrick Schumacher, for your warm welcoming words. I'm happy to be here. And I prepared a cross-section of what we are doing. As you already said, I studied architecture as well as structural engineering, which is a little bit typical for the Stuttgart education, because we have been told from the very beginning that the one cannot live without the other. So I thought, being a student, that it would make a lot of sense to understand the other discipline a little bit deeper and study both disciplines. So that yielded to the fact that I'm a licensed architect as well as a licensed engineer. But in order not to compete with my own partners, the architecture we are doing is restricted to a very small segment where typically our partners are not working in. So we are designing one residential building per year, which is always a relatively revolutionary prototype, and which acts as a, let's say, a building where we develop new technologies and where we as planners very often take a certain risk. But since the building is relatively small, we financially can cover the risk, and of course we tell the client before. So when we founded our office 18 years ago, it was quite clear for us that we wanted to work in a niche, which I said was the combination between a Porsche type level of structural engineering combined with product design. So we were probably the first engineering office ever which hired product designers from the very beginning. This was in 1992. In the meantime, we have 6 offices all around the world which all have full licenses for structural engineering, and some of them also for architecture. The team in the meantime is about 200. And as I said, with this niche thing, when we said we want to be able to solve the most complicated questions which can arise ever, then we have to have a very, let's say, scientifically high-profile teams. So me being the owner of most of the companies, we have a series of partners which are specialized in wood, in dynamics, in steel, in concrete, etc., in building physics. Yeah. We have a relatively high percentage of people holding a doctoral degree, and this gives us, especially when you have to discuss complicated issues with the administrations, a background which is more or less unbeatable. Because in Germany, if 2 professors arrive at the administration and tell that 1 + 1 is 3, they believe that. So the projects we are doing is all over the world. It goes from the Rocky Mountains to Japan. Our core competences, I would call them structural engineering. This is what we started with extreme lightweight and nicely refined structures Then we added the facade technology to it. We added green technologies onto it, not only energy saving technologies, but also water saving, resources consumption, etc., etc. Product design from the very beginning. And then, since many of our partners asked us to, let's say, develop that and to offer that a general planning capacity. For example, smaller German or other European architectural offices doing projects in Russia or in Cairo or in Dubai and so on, ask and vote for that option. In the structural engineering, it becomes now a little bit scientifically because this is the one leg I'm standing on. I think we got a relatively good name for lightweight design. And if we talk about lightweight design, and I think this is necessary to talk about it in the way I'm going to talk about it to understand why we are doing what and what is lightweight and what is the philosophy behind, I subcategorize that term and I use 3 German words because there is no equivalent in the scientific world in English for those words. So the one is Materialleichtbau, which means the search for a material with an ability which is relative to its density, its specific weight, high. Ability might be a stress the material can carry or a stiffness or whatever. The next one is Strukturleichtbau, which means structure légère or lightweight structures, but here we talk not about material, here we talk only about the topography of the single members. And the third one is Systemleichtbau. Here we talk about where the Strukturleichtbau has to fulfill only one function, which is carrying loads. Systemleichtbau fulfills several functions at the same time, carrying loads, but being also, if you look at an aircraft's wing, which is, of course, a structural element under bending and under torque, but at the same time, it becomes Systemleichtbau when it has to fulfill aerodynamic requirements or when it acts as a gas tank, as a kerosene tank. So talking with Materialleichtbau, this is what I did, for example, when I act as an architect. This was a call from the Vatican whether I would be willing to design a canopy for the Pope. So I was a little bit shocked because I went out of Catholic Church already 20 years ago, but they obviously didn't realize that, so I said yes. And I thought I would design a canopy. We finally designed the entire altar, the chair, the cross, whatever you see there. And this is Materialleichtbau, for example. This is a material we use, the dead weight of which is in the range of 900 grams per square meter. And now the only formula I will show is if we do Materialleichtbau and if we ask the one question, how much weight does it take to transfer a force from here to here over a distance of 1 meter? This means becoming light. Then we have to fulfill this formula, which is nothing else than minimize the weight, which is g, which is equivalent to this density, the specific weight, divided by an ability, for example, an ultimate stress the material can offer. And if we now look at diagrams like this ones, famous ones where you have strength versus density, you find the different material groups, and then you pick 1 or 2 in order to compare them and to find out what is the material I would have to choose if I have this force in the range of 1 to be transferred over a distance of 1 length unit. And we get a result which is, for example, steel, you need 30, whatever that is, and concrete 90. So this is what we already knew. Huh? Obviously, if we do lightweight structure, we choose steel instead of concrete. Yes. And if it would take aluminum, it would be even better, at least if we talk about strength. And if we would take titanium, we in our office, we designed the largest titanium structure ever done with Hans Hollein, 27 kilometers of titanium pipes. It would be even better. But remember this, if we want to become engineers responsible for green issues, architects thinking about green technologies, and we would like to reduce the consumption of resources, we look at this. But there's another question. In order to produce that material, you need energy. So we call that an embodied energy. The energy which is embodied in this piece of glass, which is needed to produce it. And if we now say, okay, we don't talk about minimum weight, we talk about minimum embodied energy. The formula is slightly different, but it finally condenses to minimize the embodied energy, which is nothing else than the embodied energy per unit divided by the ability of the material to do something, for example, to carry a stress. Now, another famous diagram. All the materials are shown here. We pick two, the same two as we did before, and we find out steel is 10 times more than concrete. So reducing the embodied energy in a building means steel is the hell. You cannot do that. 2 minutes before I said steel is very advantageous. So what are we going to do? Now you might say embodied energy doesn't interest me, doesn't care. We at our Institute for Lightweight Structures and Conceptual Design did some research, and we found out, for example, that in a typical European residential building, the embodied energy in the building is 30 to 40 times the energy you need to run the building per year. Means if you do what we actually do in Europe, optimize the life cycle energy by another 5% by increasing the insulation to actually 350 millimeter styrofoam if you go to the passive house technology, this is the wrong head of the hydra we are fighting at. We have to look at the embodied energy. If you reduce the dead weight or the embodied energy by 10%, this is far more efficient than to increase the insulation by another 10 or 20%. So this is something we really have to consider, and as we see here, on the one side, steel is optimal, on the other side, steel is crucial, and concrete is far better. We have a scientific problem, and this is what we are working at. So this is now work we are doing at the Institute. This is the typical bone, as we know it since 100 years, that the so-called spongiosa, which is this foam-type structure of the bone cells, those diaphragms forming the load-bearing elements, follow the trajectories. And the bubbles they are forming have different size, and where you have high loads, you have relatively small bubbles or even a totally dense material. And we asked ourselves the question, why can't we do that with concrete? We all know gas concrete, foam-type concrete, but there the bubbles have a homogeneous distribution and typically all the same size. We develop now so-called gradient concrete. This is a vertical section through a slab where you see we are still not at the end, but what we can do, we save 30 to 40% material. We have a very closed formation at the lower as well as on the upper end. And the more you come to the neutral line where there is more or less no force acting, the bubble size increases. So this is very interesting because we reduce the weight and we at the same time reduce the embodied energy. If you consider a typical high-rise building made out of concrete with a height of 200 meters, the dead weight of the load-bearing structure is typically 150,000 tons. If you would be able to save 30% of that, this would be 50,000 tons of concrete just for one building. We could take that money and put it into the facade, for example, or in other things which we want to emphasize. Strukturleichtbau. This is creating structures with the minimum weight, structures of least weight. This is something where the scientists started working on already 100 years ago. In the meantime, one came more or less to perfection. This is a sample of a cellular structure we did at the Institute. This is a sponge-type structure we did at the Institute too. This is a student work, for example, which is relatively interesting because the typical problem you face here is that you have, if you look a little bit closer to it, double curved surfaces, which are relatively difficult to be realized with standard materials. I think this is your daily problem. Huh? What we did in this sample is that we condensed them to small parts of surfaces of elements with disappearing, diminishing Gaussian curvature. So we have plane elements which are stick together and fixed with a rubber band, with a transparent one, which is more or less invisible, wrapped around those elements. and more than 6,500 of those elements form this type of structure. That relatively simple. No sheet of paper. It was designed in the computer. It was directly machined at the institute and put together by a couple of students in 1 or 2 nights. Now, if you want to overcome this, this is another research work we did. Double curved curvatures again, at least it looks like that. But if you look a little bit closer onto it, it is a sponge type thing, which we manipulated surface-wise in a way that the Gaussian curvature is equal 0 everywhere. So this is constructed out of a thin sheet metal of 0.2 millimeter thickness with a relatively complicated cutting pattern. But if you do that with a machine, hydrojetting, this is no problem at all. And then we just bend that into spatial configuration. But there's no double curvature in it. It's totally trivial and simple, and at the end it's relatively cheap. The only thing is you have to connect the elements along the corners, the border lines, in this case with a laser welding technology. So this, the know-how, this is always this ping and pong. The projects we are doing in the office, which are very often relatively complicated geometry-wise, but also construction-wise, and which ask for new solutions, are brought back to the institute where we research with about 26, 28 researchers doing their doctoral thesis at the institute, and where we develop, for example, technologies where we condense complicated double curved surfaces into what we say an approximation of that curved surface with Gaussian zero curvature elements. And this enables us then to do very complicated buildings like this one. This is an excerpt, just a part of a length 30 to 40 meters of an exhibition stand for Audi. Christoph Ingenhofen was the architect. In total, this, what you see, shell-type wall is 300 meter long. It's undulated in plan, and it's curved in vertical sections, so it's a double curved surface everywhere, totally irregular. And we said, okay, this is Audi, and on the Frankfurt Motor Show, Audi is directly between Maserati, Ferrari, and Porsche. So we somehow have to capture the clients and keep them in a wall, so that they don't look at those cars. So we built this wall, a transparent wall with a length of 300 meters, 6 meters high. And again, the question was how to do that. The structure is minimized. As you see, this is this diagonal grid of 50 millimeter diameter stainless steel pipes. And then there are 13,500 triangular pieces of glass, which had to be installed within 96 hours, 13,000 pieces. At the very beginning, most of them were all different. And then we said, okay, the gap between the pieces was defined to be 4 millimeters. We said, if we allow, in a very complicated mathematical procedure, the gap to be between 3.5 and 4.5 millimeters, and if we allow a certain deviation of the coincidence between the gap and the stainless steel pipes of a few parts of a degree, then we could write an optimization program which breaks the number of various elements down to a minimum. And at the end, we had only, I think, 350 different pieces of glass. And this was all prefabricated, loaded into a jumbo, flown to Tokyo, and installed within 4 days. There was no chance for any repair or rethinking. And if you look at this detail, for example, what you see on the left-hand side, this is 2 of the crossing stainless steel pipes, spatially curved. There's one detail which covers all the thousands of geometrical situations. And again, we worked on that detail, I would say 5 engineers for 4 weeks, for a 200-gram detail. But at the very end, it was one detail which covered every problem. Instead of having 250 different details, which might be manufactured wrong with a mistake, an error, etc., etc. And then, of course, stainless steel, machined automatically and installed, this is important too, by one worker with 2 hands. There was no third hand needed. There's one single bolt which holds everything together. So, very comparable to that. This is another, it's a cable net roof, double curved. The first application ever done, we got a patent for that, where we applied glass shingles. So normally, if you have a plain roof, square meshed, it's very easy to be produced, relatively cheap. If you then take the square mesh roof and bring it into spatial configuration, the square-sized meshes become diamond-shaped. In this case, we would have had, I think, 42,000 different diamonds to fill out with glass. So you could say, okay, if you survive the Audi exhibition stand, then you will survive that too. We said, now we want to introduce another technology. We know how to do it, let's say, in a smaller variety of geometries, but here I said we want to have one glass pane. And if you have one glass pane, then you have to develop a shingle technology where you lift the glass off the cable net plane. This is what we did here. So this is square-sized elements held in place with a stainless steel wire. It gives a very nice appearance, like if a spider would have woven a web. And if you look a little bit tangential into the surface, then you see they're overlapping. So of course we had to do rain tests, wind simulation, etc., in order to guarantee that the wind does not drive the rain under the shingles and makes the people wet then. But in that case, it works perfectly up to 50 kilometers of wind. And then we said, okay, since this is an open space, if the wind is beyond 50, nobody won't be there. This is in Bad Neustadt. It's in the deep Bavaria. You really have to make a decision to drive there. You even lose handy connection on the way. See, in the technology here, we applied here, which is a building with GMP, a huge maritime museum in China, close to Shanghai. We again have a cable net. This, you see the two sails. The top is about 65 to 70 meter high, so it's a huge construction, as you see here. Huge shell-type cantilevers, and the glass skin, which spans between the two shells, is about 60 meters high. And again, it's a cable net, double curved. The meshes are, of course, diamond-shaped again, and the four nodes of the mesh are not in one plane, so everything is double curved. But here we did a form-finding technology where we guaranteed that the warping of the panes, if we have a plain sheet of glass and fix it at 3 points and then squeeze it onto point number 4, is such that the glass does not break, which then yields to this type. Yes, yeah, this might move, I would say, up to 200 millimeters, which is no problem at all. 200 millimeters plus minus. You will see an example later on where the facade moves 400 millimeters inside outside.
And the forces? The linear forces?
They are okay. The cables in that Lingang museum, they are, I think, 10 or 12 millimeters, which is modest. And the pane size is close to 800 millimeters, which is very economic, very modest. So this is one of the largest facades ever built. This is 40 meters high and 1,000 meters long. It's a cable supported, minimized material facade for the airport in Bangkok, where we did all the above ground engineering. And that the concourses are able to load, unload 64 wide-body aircraft at the same time. And what is interesting, the concourses are covered mostly with textile. In this very hot climate, very humid climate in Bangkok, at the same time, the new runway is relatively close. And in Thailand, also the aircrafts are still allowed to land and to start, which emit a noise which is in the range of 110 decibel. Those aircrafts are even not allowed to cross, to fly over Europe. So we had an acoustic problem and we had a thermal problem. And the question how we solved it, again, we said we want to minimize the electric energy to lighten the building. So we want to have as much as translucency or transparency as possible, but we have to keep away the heat. The technology applied here took us 2 years of research, privately financed, 4 disciplines, an acoustician, an energy specialist, the facade and structural engineer, plus the architect. And what we developed is a 3-layer compound of textile. The outer one is a traditional glass fiber Teflon coated to keep wind and dust and rain away. Then the intermediate one is a very thin cable net infilled with 5mm polycarbonate, which is totally transparent but has another weight, another specific weight. And the lower one, which you see here, the inner layer, is a semi-open weave glass fiber coated. And the new thing here, this is coated with a low emissivity coating. That means low emissivity. You know that from the flat iron at home. Nobody ever knows whether the flat iron is warm or cold. So housewife typically, by approaching your hand, you don't even feel that. So what you do is you make this, or this, then you know. So the flat iron is 200 degrees hot, and you are not able to realize that because it does not emit warmth or energy. And we took this effect, which occurs with aluminum, with stainless steel, and a couple of other toxic materials. And we said, if we would be able to transfer this effect from the flat iron's aluminum onto the textile, then this textile could be warm or even hot, but it would not emit warmth. So the idea was then to have the roof in 27-meter height to allow for a temperature of up to 60 to 70 degrees over there, but to have a clear stratification of the air. Cool, fresh air where the people are, and then it's getting warmer and warmer and warmer up to 60, 65 degrees at the top. So the material is hot too, but it does not emit. So you will feel fine. This is the problem the car producers have. If your car stands in the summer exposed to the sun, the car gets hot. You step in, you switch on the air conditioning, you have cold air, but you're still sweating because the radiation, which is 50% of your comfort feeling, is still warm. And the air temperature, which is the other 50%, is cold. So that contradiction which happens in your car does not occur here. No, zero. The air in between the three layers, which is between 200 and 400 millimeter from layer to layer, that is a certain convection. Yeah? And the big trick is this low E coating on the lower membrane, which has the thickness of one molecule. Huh? So this is typical of how we work. Yeah? So we have the problem, and then we say, okay, we do not circumvent it, we solve it. And then work like hell for so and so long, typically with different disciplines, and then that's it. Or if you look at this, this is one of the, we call that cable stayed facade. My academic teacher, Jörg Schleich, he invented the so-called cable net facades, which is a vertical as well as a horizontal series of cables, pre-stressed. The big disadvantage of that is that you have horizontal pre-stressed cables which have to be anchored in the building and which are relatively high. So it might occur that you have a horizontal force of 100 to 300 tons per floor at 10th floor, at 11th floor, and 12th floor. And this takes a lot of structural, let's say, effort to bring those loads down. So we said, if this is the problem, if the horizontal cable induced that problem, we just leave them off, then there is no problem. So this is only vertical cables. We call that also a harp type of facade. In this case, this is for a museum in Hagen in the northern part of Germany. There's also a heating pipe introduced in the sealant. Therefore, the sealants are a little bit thicker than normally. But what we did with thousands of square meters with these vertical cable facades is that you typically have a facade up to 20-25 meters high with a cable spacing of 2 meter, 2 meter 50. The thickness of the cable is 20 to 25 millimeter diameter. This is just my thumb. And they are pre-stressed, faster. We have that with single layer, double layer, insulated, bomb blasting, all the problems.
The load imposed on the roof. Because we have a project where we would like to do that.
Yeah.
About it's a large opening, cantilever to that point, or bridge. So
there are solutions for that. Of course, there's a vertical force acting at the very top, and now you need a clever element where you bring this vertical force backwards. But since you typically have minimum a pair of columns, if the force pulls down here, you induce a higher compression force here, and you reduce the compression force here.
This kind of tall glass wall to pull down, how does it compare to snow load on the roof or to light load on the floor?
What would we say? We have about 10 tons, 5 tons per meter, 5 to 10 tons per meter. So it's a remarkable size, but I would not fear it. I would not fear it. We did such roofs, for example, or such facades where the main load supporting columns had a spacing of 40 meters. And then we introduced something in the facade which transfers these vertical forces onto those columns. So we did at the Europäische Investment Bank in Luxembourg, also Christoph Ingenhofen project. One can do that relatively elegant. And here, look at this. This is so transparent that you don't see any structure. If you look a little bit closer, you see the thick vertical sealants, and behind them there's this tiny gray thing. This is the load-bearing cable, that's all. This is Museum Hagen. So of course, if you have a heavy wind load, let's say 100 miles an hour, this facade bumps inward about 300 to 400 millimeters as well as outward, but relatively slow, so it breathes. And you have to do a turbulence analysis, what we are used to do, in order to guarantee that the thing starts not vibrating too much. But in the meantime, we have 14 years of experience with that, and many of the facades, one in Bremerhaven, they had a Stadtgarten, a city garden with 100-year-old oak trees filled up. The storm was so tough that all the oak trees fell down, but the facade did not even show any crack, because it just deformed, deviated the action. And there you have these horizontal cables too. And these induce such high loads that you don't have big windows on the facade sides. This is a very simple, low-budget parking garage where we provided a shading element for the top, which is nothing else than horizontally spanned cables. In order to avoid that they start dancing under wind load and wind turbulences, we introduced this thick pipe, which encloses also the lighting and which is then filled up with concrete in order to provide some dead weight. The rest is relatively simple. And I think quite charming, the result, and very cheap. And there are more complicated things like this, the Mercedes-Benz Museum in Stuttgart, where we did the entire engineering. I would think one of the more complicated concrete structures ever built. It's more or less all exposed concrete. And we did the entire building in 3D, of course. So this is the typical type of drawing. There was 1,500 different window sizes. There was not much space for taking up tolerances, etc. So everything had to be very, very precise. Yeah, of course, our experiences, they go up to high rises with a height of, actually we are designing one with 380 meters in China. We already designed some which have not been built in Ras Al Khaimah with 850 meters too. And then Systemleichtbau, this is when it comes all together. Yeah? When we combine the Materialleichtbau, minimizing the embodied energy or the specific weight or whatever relative to the ability of something, and introducing lightweight structures principle too. This is the first project I did. So when I left university, I fell into that. It was in the southern part of France, in Nîmes, a project which had to fulfill French codes, but the project language was English, with the only problem that I was the only one who spoke English, and all the other ones spoke Italian and Dutch and whatever. So it was a Babylon on site. But the interesting thing is this is a temporary structure which had been built into the Colosseum for 14 years, always in October, installed and taken out before the tourists came in April. It was a temporary roofing over the winter time. It was the largest air-inflated cushion ever built. So the span, the clear span of the white cushion is 60 by 90 meters. It's 1 millimeter at the top, 1 millimeter on the bottom, and it's air-filled with a slightly overpressure. And it had to resist more than 200 kilometers of wind speed and very heavy snow loading, which nobody expects in the southern part of France, but which exists. So this is building with air then. Yeah? You use air as a structural element. And so we said, okay, if we use air in the inflated, air-supported structure, we might even become lighter if we avoid the air. But this means working with vacuum. So what you see here is the first vacuum facade ever built for an exhibition stand. Small piece so that the risk is limited. We did a design for Mero. They are famous for their space structures. And they asked us whether we could open or help them to open new markets. And so we developed a shell type Mero thing where you have just a single layer. And they were so happy about that they want to have an exhibition stand with that. The only question was, what do we do with this relatively rigid Mero thing? So I said we have to throw a big negligee over it. What we finally did, so we bought a relatively cheap PVC plastic film and we glass powder blasted that. And we fixed it on the lower edge, threw it over the thing, which is in total 5 meters high and more than 30 meters long, and fixed it again at the lower edge too, so that we had a closed volume, and then we sucked out the air. And we oversized the bag, the plastic film, because we wanted to have those wrinkles and folds, which added a lot of, let's say, aesthetical, tactile qualities to it. People love to touch that. Yeah. So, but with this, we got all the experience needed to build vacuum facades. I will come back to that later on. This is another sample where we are fighting with since years that somebody wants to have a residential building which looks like a soap bubble made out of glass with a clear span of 25 meters, and we are unable to do that. Since the year 2000, we have this request and we are unable. So we are researching, of course. This is the first outcome, the first glass shell which is totally glued, no metal collections. In that case, it's 8.50 meters clear span. The thickness is 10 millimeter. So the ratio is 1 to 850, which is far thinner than the ratio you find in an eggshell, and which is close to working with paper. And crawling below it and looking upwards is absolutely fantastic. So, now facade technology. We did glass and other facades for many buildings. This is one example, more or less totally glazed double facade for the Deutsche Post Tower in Bonn, with a huge series of flaps which can be opened and closed automatically depending on the wind speed and wind direction, so that the wind stream between the outer and the inner layer of the facade is always such that you can open the inner windows and stick your head out without running into the problem that all the paperwork flies away. This is a facade we did in Washington with load-bearing fins exposed to the outside, glass fins. That's all load-bearing glass there. And this is one of the, that's quite a nice project. I'm a friend with Finn Geipel, who is a German architect working a lot in France since more than 20 years, and Finn and I, we are doing most of his structures or his buildings together. This is the newest one, La Cité de Design, in the southern part of France, in Saint-Étienne, which is the first building of a huge area, which is the French center of design. It's typically French. Huh? There's always a center, and they call this Saint-Étienne the French center of modern design. So they're installing a design school there, a museum, and so on and so on. And this is the first building, which has to fulfill all those functions for a couple of years. So it's a monospace, means a one-room building, 200 meter long, 40 meter deep, 8 meters high. And if you look at it, we did it absolutely light. And we created a surface, which is the outer facade, as well as the roof, consisting out of 14,000 triangles. And they all have different functions. Some of them are just there for insulating and waterproofing. Some of them are there for collecting energy. We do that with photovoltaic, but also photosynthetic. Other ones have switchable glass. Other ones have the so-called zebra pattern, which is insulated glass with a third layer in between. And you have a stripe type painting or printing onto them, and by shifting the intermediate piece, you can shade the elements. Some of them have colored glass and so on and so on. It's very, very nice. So this is, as I said, some of the triangles are switchable glass. This is a patent we have where we developed switchable glass, which is not based on organic material. There's two types of switchable glasses on the market. The one which is based on organic material, this cannot resist temperatures higher than 90 degrees. What we measured is if you darken the paint totally and expose it to sunlight relatively long, 3, 4, 5 hours, then you have these 90 degrees. And then you run into the problem of chemical degradation. The system we are working with is just based on, let's say, on non-organic material, which switches in real time and which can provide a shading coefficient in the range of 50%. So you start with a 50% translucency and you can make it totally dark, or you start with 70 and you can reduce it down to 20% transparency. This is something we are working on. We test that since 6 or 8 years. It's absolutely robust, and actually we have a huge research contract where we transfer that technology to floor high paints. This is another example. For the facades we are doing, this is the first real vacuum facade, outdoor. So this is one of the saddest places in the world. It's a concentration camp Sachsenhausen in Germany, which is a national monument, and which, due to, let's say, degradation caused by weathering, had to be protected with a building with a clear span in the range of, I think, 40 by 50 meters, column-free, which is something. The architect was Hans-Günther Merz, and we said, okay, 40 by 50 meter will provoke most of the teams to come up with architecture, with engineering sensations, underslung, suspended and whatever, and we said, we have to do that totally modest. No structure, no detail, no single bolt visible, just plain surfaces. And how did we solve that? The building is a very cheap and trivial steel truss, spatial truss. On the surfaces of it, we installed gratings with an opening, creating a mesh of 30 by 30 millimeters. And then we fixed at the lower lines huge pieces of fabric, the lower end, and threw them over the structure, again formed this closed bag, and then evacuated the space in between, so that all the facades, the top, the vertical, as well as the ceiling, are sucked onto those gratings. So this gives you the chance to provide more or less detail-free, huge surfaces. And if you now imagine that this translucent ceiling is held in place by negative pressure, a very slight negative pressure, I think that's quite fantastic. Because if you now transfer this idea to double curved surfaces, which are sometimes so easy to be created and so on, you can take the advantage of the textile technique, where double curved surfaces are a self-understanding issue, it's daily work. And if we then fix the stuff, for example, with negative pressure, you can do more or less everything. And from a recyclability standpoint, which is one of my hobbies too, this becomes very interesting because you can decompose the building by switching off the pressure pump. Just push the bottom, and then the sail slowly falls down, and you take this one, have material number 1, you take the steel structure, material number 2. We have mono-material, Ein-Werkstoff components. So of course, we further developed those things, not only plain surfaces, but introducing origami patternings, wrapping them over structures, applying the suction, keeping them in place. And this is something what we are working to in textile facades, that we say, okay, We want to take advantage of the breathability, of the deformability of the material. So what we did here is we introduced pneumatic muscles, a very special type, but imagine you have a plastic pipe which is relatively stiff here and relatively soft here. And then you inflate it with pressure. Then, of course, the soft part elongates and the other one doesn't. So it bends like this. Huh? The soft part gets longer, the stiff part doesn't. So this is what we did here. Yeah? You have two pairs which are pressure inflated with pressure, and then you increase the internal pressure, and then they form this double banana thing. Yeah? So you can open the slots in real time. One example for several solutions we investigated and researched on in breathable facades. This is what we call meso type of openings. Meso is 1 to 100 millimeters. These ones are about 80 millimeters. Another research goes to micro type of openings, which is below 1 millimeter. Micro porosities, which are switchable in order to transport humidity or air or things like this. And this makes us keen enough to propose high-rise buildings, of course, with a textile skin. Multi-layer textile skins, etc. Then another thing, green technologies. Product design and general planning, we run through that relatively short. I think green technology might be interesting for you. It has something to do with the history of our work. When we started with very, very light structural engineering, it became quite obvious after a year that we were able to do the load-bearing elements of a 10-story high facade as thick as a thumb. And then the people from the facade technology came with their thermo breaks and whatever profiles, and then the insulating profile was that. Totally messed up our refined engineering here. So we said this is no longer possible. We have to go into that business too. So this is how we came to the facade technology. Just ensuring that our structural solutions are not messed up by the facade people. Then, but doing these facades, we always, let's say, had to work with the people from the building physics thing, huh? Thermal flow, and so on and so on. And it didn't take that long, and then we said, okay, I think we have to do that ourselves. Because the solutions proposed typically by the partners were not the solutions we were expecting. So we have been building up a group profiled in that field, but not only energy saving, also water saving technologies, green technologies in the widest range. So what do we do there? I think this is a very nice example. This is the building I'm living in. So this is one of the residentials we designed, one per year, where I'm acting as the architect. This is probably the first so-called 000 buildings ever built. 000 means does not use fossil energy, has 0 emissions, and 0 waste means 100% recyclable. Since that time, we developed a technology where we, let's say, are able to design buildings which are fully recyclable. Okay, now everybody will say, we as architects, we build for eternity. That's clear, we do so too. But most of the buildings we designed, in the meantime, underwent some changes, especially airports and so on. And if you look then what happens there, when they pull out all the material, which is nothing else than waste, or sometimes also toxic waste. And if you go a little bit to statistics, which say in Central Europe that 50 to 60% of the mass waste comes from building industry, then we have to remember that we, being architects, engineers, have a responsibility for the upcoming generations. And if we know that we are using that much resources and that we are producing that much waste, and very often toxic waste, if you think on all the sealants and the silicones and whatever and the paintings, then we have to do something. And therefore we developed since more than 10 years these technologies. So it's totally recyclable, but it doesn't look like that. Okay, the left 4 pipes, yeah. This is the right 4 one, this is a fresh air supply. The building is a glass box, 4 stories high. The floors are always interrupted, so it's a monospace. If you stand in the 4th floor, you can talk to somebody standing at ground floor. And in wintertime, the building is absolutely airtight because we have to be very careful with energy. So we protect every joule we somewhere got. And in order not to die by our own exhalation, you need a minimum of fresh air supply in that phases. And this is why we have the 4 pipes on the right-hand side. So this is fresh air which we get from the garden and which we warm up through a 36-meter long pipe running in the soil. Then it passes a heat exchanger and then it blows the fresh air into the building. In the left 4 pipes, this is rainwater from the roof and the water supply, electricity, communication. This is what we could call Nervenbündel. This is the bundle of nerves which you need. There is no other vertical connection between the floors except the columns. Everything runs in those 4 pipes. Famous is the bathtub, which you see here on the this is the bathtub. It's on sliders. So if you decide to take your bath somewhere else, you just uncouple the fast couplings. And since we have everywhere around the facade these aluminum channels which have flaps to be opened, if you open them, you have water supply, warm, cold, wastewater, electricity, communication. You just unplug it, pull the thing to another corner, plug it in, and take your bath somewhere else. Now, this is the optimum place. I found that out. See, the idea is if you want to design a building which is recyclable, then you are not longer allowed to, let's say, to install the wiring and plumbing in the wall. Because nobody will pull out the copper wires. Never. Now, we did some research and I asked the question, how much copper is in a German office building? So you take 1 ton of German office building and compare this to 1 ton of stone you get in a Chile copper mine. Chile is the world market leader in copper. Very interesting from the marketing and so on, copper mines. So what would you say? You have 1 ton of stone from Chile with some copper in it, and we would say, okay, there's 100 units of copper, whatever a unit is. How much is in the German office building? After taking all the laptops away, just the wiring and the communication and so on, electricity, is 40%. Now imagine, in Germany, you have the copper in front of you. In Chile, you have to blow it out of the mountains. You have to fraction the stone, you have to melt the copper, you have to transport it over the sea. So it makes a lot of sense to ask the questions, why don't we reuse the materials we have somewhere there? But if you ask that question, then you are probably permanently failing and hitting all the Dachdecker-Richtlinien and Elektrohandwerk-Richtlinien and so on, because you have to come up with new solutions. And when I said, in this building, since there is no wall, I have no chance to hide any wiring or piping, it's all open, it's all accessible, so it's all easy to be decomposed, you have to develop a lot of new solutions. Some of them are very advantageous, because here in this building you have everywhere warm, cold, and wastewater supply, so you can put your bathtub everywhere. If I decide tomorrow to put the kitchen in the floor number 2 and the bath in floor number 4, this is no problem at all. I do not need the plumber. And some of those technologies, we apply them. For example, this is a building Hans Hollein designed already in 1966, and then he resubmitted this in a competition and he won him. I think this is typically Hans Hollein. It's so great. It's in Shenzhen. But again, we are doing the entire green technology, facade technologies, and so on. It's a, let's say, very strict energy saving issues we have to consider there in this very delicate climate of high humidity and so on. So it's complicated. How do we do that? We have a variety of approaches and computer programs. Of course, let's say summing up the solar radiation on different surfaces over the year is the most trivial thing. Everybody knows that. This is a little bit more complicated, a little bit more unique selling point. So this is now the marketing thing. We are able to design city blocks or certain buildings within a city block in a way that we take advantage from daily or seasonal winds. So we open and close certain parts in plan so that we accelerate or slow down the wind, which means the wind can warm up the surface or can cool down the surfaces, which yields to remarkable results. But being able, in order to be able to do that, you need a numerical wind flow analysis. So this is now one of our partners. He's probably Michael Bruce, one of the best in doing those simulations. And this is more than a numerical wind tunnel, because here we do not only simulate the wind flow, means speed and density, you also simulate the energy content of the air. So we talk about temperatures and we talk about humidity. And this finally, and this is also a Michael Bruce device, yields to computer programs where we are able, plus minus, to predict the comfort feeling of human beings under certain situations. So there are some typical bots, as they are called. This is one, walking, I think this is in Abu Dhabi, from the exposed into the shadow. And you see on the right-hand side the transpiration rate of Steve and the skin surface temperature and the heartbeat frequency and whatever. Yeah? So the longer Steve walks, or this is Aaron, in the sunlight, the warmer it gets, the more uncomfortable he feels, or she. And this, at the very, very end, gives you a clear indication on what you have to do with air temperature, radiation, shading, and things like this. So it does not make any sense to cover entire Dubai in order to provide a comfortable feeling to the people. But the question is, how much of the streets should you shade? What should be the radiation temperature? Can you, for example, install here surfaces which radiate less temperature? If you make all them black, then you have the hell. If you make them white, or if they store the energy until nighttime and release it then by using phase change materials, etc., then you can provide a much better comfort situation in between the buildings. So this is not only indoor, this is an outdoor application of what we are doing here. And then of course here, so German car industry by law has to guarantee a recycling ratio higher than 85%. If you would ask a contractor on the other side of the street what his recycling ratio is, I think he would get a nervous breakdown. And you could close up the entire German building industry if you would ask even for 20%. Because there is not even an understanding of the term. There is no planning technology to design buildings in a way that you can take advantage from recycling certain materials at the end of lifetime. Everybody's talking about reducing the lifetime energy consumption. Nobody's talking about embodied energy. Nobody is talking about resources or waste. But this will become an issue. The people I know from the European Union, one of my clients, once I have a residential building, is one top person of the European Union. He says that they are planning to introduce laws relatively strict, latest in 2020, clearly prescribing recyclability ratios for the building industry. So knowing this, we are going to prepare ourselves so that we, when it comes to the point, have the nose ahead to all the others. If you look at a typical Central European building, easily you find between 15 and 25 different materials glued and sticked and plastered together. There is nobody in the world who will split them up into their initial components. So this is all special waste. And the more passive house we are doing, in Central Europe, the more styrofoam we are adding, the more toxic waste we are creating. What we evaluated at the Institute, very interesting research work, we asked the question, how much energy does it take to produce styrofoam? And how much energy do you save in a 50-year lifetime period in a residential building with the styrofoam you put on the facade? And there's a very clear indication that beyond 15 centimeters, it's all nonsense. It's all nonsense. Because it takes more energy to produce it than you save with it. 15 centimeters. Actual passive house technology is close to 300 millimeters. So of course, we contributed very much in the Deutsche Gesellschaft für nachhaltiges Bauen. I'm one of the co-founders of this, which is nothing else than a big pot where we collect all the know-how and how to design buildings in a way that will reduce energy consumption, resource consumption, waste production. Product design, just one thing. So we are working with the world market leader in the cable cars, which is Doppelmayr. It's obvious, huh? What they need is very light cars so that they minimize the weight to be transported. People are getting permanently more heavy, so they have to reduce the weight of their cars. So they need us. Huh? This is Systemleichtbau. Huh? Multifunctional. And with the general planning aspect, I already mentioned that. This especially comes from our Moscow, Cairo, and Dubai office, where we have architectural as well as engineering licenses, but do not work as architects. So especially smaller practices asked us whether we could provide them those licenses and act as general planners with them, and this is a very fruitful cooperation. So thank you so much.
Thanks.
Of course. I'm not allowed to answer how much those residential buildings cost, but I answer every other question. Yes. No, not really. It's the Energieausweis. And the Energieausweis is what we say, it's a little bit of shot in the oven. Huh? Means it was a big action, which in the meantime became a little bit dubious since you can buy the thing via internet for €12.50. It was a big action which turned out to be totally unfruitful. And what we did with this DGNB certification system, which is in a certain way a competitor to BREEAM or LEED, but only in a certain one, is that we said we have to take into account more aspects than just energy saving. So all the recyclability things and so on, the life cycle energy consumption, that's all embedded in that. But in German market, the Energieausweis is, nobody cares. Yes. Yeah, yeah. This is what we are going after with the DGNB. Yeah. This is when the European Union intends to introduce restrictions or laws or codes or however this will be called, which limit. So for example, the one already well known is that all the residential buildings beyond 2020 have to be zero energy buildings. Or to be correct, zero fossil energy buildings for life cycle consumption, not for embodied energy. Not yet, but it comes. This consciousness arises. You can clearly feel that. When we founded the DGNB 3 years ago, everybody said, why are you doing this? You are totally stupid and whatever this is. There's lead and there's pre-am and nobody wants to use this, and why should we have a German thing? And we said, it is not our intention to create a certification system. It is our intention to base the know-how we have on a, let's say, scientific footing, scientific foundation, and the responsibility of academic teachers to identify the white spots in the map of know-how. And once we did so, we identified so many white spots that we sat together and we said, okay, if we ask for public funding for research, it would be in the range of 30 to 40 million euros to cover those problems. So it was quite obvious that there was no chance to get that money. Then we said, okay, then we form an initiative from the bottom up and founded this society, which in the meantime has 900 members. Firms like Audi, Mercedes, Deutsche Bank, and so on. And we're actually more than 320 people, top people from the research in Germany, are contributing for free. It's all on a free of charge basis to cover those white spots. This, within 3 years, yielded to the situation that a know-how has been assembled there, which is incredible, which is so big that many other countries want to overtake that. For example, countries like Bulgaria or even Russia. I had talks in Russia 3 weeks ago with the president of the Russian Chamber of Architects. They said, we are totally unable to develop that. On the one hand side, we do not have the know-how. On the other side, let's say we do not have this bottom-up movement. And if we do research contracting with our universities, this will never yield to an end. So why don't we somehow join and cooperate, and we take all your know-how and adjust it to Russian thing, or Russian standards, or Russian whatever situations. Which is very interesting, because it opens also certain markets. And President Medvedev, he announced that up to 2020, Russia has to reduce the energy consumption by 40%. This is one thing, and the other one thing is that the Russian politicians have heavy problems with young people fleeing the countryside. But countryside is there where they have their sources. This is agriculture and mines and all those things like coal and oil and gas. And all the young people flee the Siberian and whatever areas because it's, for them, uninteresting. The architecture there is zero, culture zero, sports zero, there's nothing. So what is left over is people beyond 40. And as we know, typical Russian man dies with 59 average. So this is an economic problem of an immense impact. So what they decided is to make the countryside attractive again by rebuilding as much as they can, installing culture, sport, and whatever education, and bring the young people back to where they came from. And this sustainable architecture thing is a very important part of it. Not declaring it sustainability, but making it attractive. So it's a huge market even for us. Not today, but maybe in 2 or 3 years.
Airflow studies. Looking for environmental parameters to work with, because sun shading, some radiation maps, using that as it was quite easy. The next thing that we really, which also could have real impact on urban morphology, is this airflow thing also interest perhaps to let some of that air flow through a building, courtyards. But it seems much more difficult, obviously, to get the right intuition and the handle on simulating that.
Yeah.
So one route, you're working with also the University of Vienna and trying to build a kind of expertise study of the different vernaculars of this world, where you have Fourier definitions, architectural structures, morphologies, responding to climatic conditions and creating degrees of comfort without those so it's quite interesting. One that we could elaborate on, select particular projects where we can work with your expertise on generating architectures to take advantage of creating winds.
Yeah, that would be wonderful. Yeah. It is not that simple as it sounds. Yeah.
There seems to be a lot of just wanting to raise it if we would like to do this, but it definitely helps to do that with a greater asset.
So the people around Michael Bruce or in our green technology department, I think they could assist and they could help.
For instance, on a competition,
Yeah.
Maybe a relatively small building, like you might have a study where winds are channeled over.
Exactly how we can manipulate them.
Yeah. Ventilation, but also, as you said, for taking away heat.
Yeah.
The whole kind of building physics, energy. And also, I'm looking always for opportunities where this environmental activity has architectural impact in terms of morphology, in terms of tectonic solutions, builds which capture window openings, rather than solutions which are buried in the ground.
Yeah.
They're engineering. I think there's a lot of environmental adaptation we can do with, which gives also visual impact, makes visible.
I'm very sure that there is.
What I'm looking for wind, particularly for such I don't wonder what else that could be. This one is what I would like to push forward.
One, for example, we came up with is acoustics. Everybody's blaming about whatever the noise level caused by traffic. The architecture does not answer it. The only answer architecture has is heavy glazing. If you would have facades which absorb the sound, it could help a lot, of course. But sound absorbing facades is a word which has never been taken into any architect's mouth up to now. But if we aggressively attack all those questions, like taking advantage of prevailing wind directions, of the temperature of those winds, of the humidity content, of the fact that a facade can do more than just being watertight and airtight facade, but can reflect the sound, can absorb the sound, can provide shade even to the street level, etc., etc., then I think also the architectural language will be influenced very much.
Yeah, we should work with structural design. These are things that are extremely interesting to us and competition research. And I can see, I mean, we also doing the DRL and tower research focusing on the skeleton as the primary subsystem. How this differentiates of the tower. And looking at the solution also, disengaging it from aspects of circulation of the planet surface.
Yeah.
I was very interested in one of the towers that I'm working with actually with a kind of tensile stability system on the outside, which would then connect quite well with the cable net.
Okay.
So things like this, I'm just wondering how far these can scale, whether it's feasible. Anyway, I would invite you to join maybe one of the competitions.
Yeah, this is
innovative high-rise structures.
This is what I just wanted to say. I think up to now, I never had a general recipe. It was from time to time, from project to project, it differs. But the way we work is typically from the very first second on, because if the building is already established, we cannot contribute that much. And don't hesitate to give us a call when you start doing a competition or whether you need some consultants or an idea or so. The different disciplines in our office, might be represented in a very first phase of a competition just by one or two people, like Benjamin Baer or Martin Sinold, as they are here. I think Benjamin can cover structural aspects as well as facade aspects, where he is the absolute specialist, and Mr. Sinold is one of the specialists for textile technologies, but also for... Yeah.
That was the facade, it wasn't the...
It was the facade. This was keen enough. Yeah, so...
And the breathing facade, is that...
That's under research. Yeah, there's also some patents already which are pending, which we hopefully get. But this is out of this 26, 28 researchers at the Institute, I would say 10 to 12 are researching in facades made of textile, multi-layer textile systems. Yeah, this 2-year development of this low E-coated textile we used finally in Bangkok airport was possible only since there was so much corruption there in Thailand that they interrupted the planning process so often that it finally took 12 years. So we had plenty of time to develop that. In a normal procedure, you can't do that. But being 200 engineers means that we typically have about 50 to 80 projects at the same time on the drawing board. So there are so many problems which arise and where we say, okay, we can't solve them now, but let's solve them parallel to our daily work, or let's talk to other people specialized in those whatever things, so that we, from then on, in a parallel process, develop that. So this building does not get an answer, is executed in traditional technologies, but we drive those problems to an end. And in some cases, it takes 5, 6, 7 years to develop that. There's a very famous example of the so-called rotating umbrellas. It's a nice story. You should see that because nobody believes that. We once had a client who came and said, Mr. Sobek, I want to have 10 or 20 umbrellas, 15 meter diameter, made out of textile, and I want to have them next year. It was German Telekom, one of the richest companies in Germany. I said, I'm so sorry, but the world record in umbrellas made out of textile is just hitting the 30-meter diameter barrier. And there you have to have carbon fiber spokes reaching out from the central post with titanium hinges and so on. And if the wind blows too hard, then you have to close the umbrella. And I said, this is not what I want to have. I want to have them for Hanover in the northern part of Germany, where we have a lot of wind and rain. So of course, then they have to stay open. I said, I'm totally unable to do that. So he was totally angry because he came down to my office to offer me that project. And I declared to be unable to do that. I was angry too because I missed the fee. So this then drove me, I don't know how long. And then we said, okay, the only problem limiting the size is these radial spokes. The central mast, you can make this as fat as ever. And the textile is not a problem at all, but the spokes. And we did not find any solution to overcome that problem with the spokes. So I said, if the spokes are the problem, we leave them off. This was quite clear. But the problem then was how to design an umbrella without spokes. And then we invented working with centrifugal forces. So we set the piece of textile under rotation. This was perfect. So there were periods where we owned more than 100 umbrellas. That size, 20, 25 square meters and even more. Then something happened which is very interesting. Up from a certain diameter, 1.50 meters or so, those umbrellas took the shape of what the mathematicians call an ape saddle. So 3 times up, 3 times down. 2 for the legs, 1 for the tail. And independent from the rotational speed, this ape saddle was stable. The fabric was rotating, but the thing was stable, or it turned against or with the rotation, but not with the rotational speed itself. So it was something like from a magic hand turned backwards and forward while the fabric was rotating 1 time per minute. We had no chance at all to overcome that. So at the very end, we introduced lead in the perimeter, like grandma does with the curtains, so have them hanging down straight. This, of course, worked. And we did a long time test, and after 2 weeks, when I came to the test site, the lead just flew away. So we said, this is far too dangerous. And then we invented something which is, in hindsight, very trivial. If this is the end of the textile, we form cross-section shape like this. So we bend it inward. Because what we realized is when it was rotating, due to the very tiny friction between the air and the rotating textile, the air was sucked up and thrown outwards. So we said, if the air is thrown outwards, we capture that in those pockets, and then it probably will pre-stress the umbrella. And this occurred. So we are totally happy. We submitted a patent. I went home, told that, totally proud, to my son, who was 6 at that time. He, eating a sausage, interrupted and said, Papa, you should have looked at a Frisbee. But however, so this was one of the most fruitful projects we ever did. We did not make any dime out of it. It took us several years to research it, but what we learned in working with those dynamics, and ultra diameter fabrics and working with friction and centrifugal forces and so on, finally enabled us to do other problems, to do other projects, which were considered to be unsolvable. For example, especially those cable facades which move so much. We designed such a cable facade with insulated glazing for the airport in O'Hare, and we submitted all the drawings 1 week before 9/11. Then 9/11 occurred, we never heard anything, and 1 year later, they called us up and said, okay, now we want the facade bomb-proof. I said, which bomb are you thinking of? And they said, you are the engineers, you have to propose a bomb. So we said, okay. First of all, I'm a total anti-militarist. Okay, if we have to do that, we assume a bomb about pocket size. Did an analysis. Interesting-wise, the 2 groups of specialists in the world, the one is situated in Israel and the other one in North Ireland. So we consulted them. And then we did this very complicated dynamic analysis, and then we told them, okay, the facade stands as designed. How big is the bomb? That's too small, make it bigger. So after 3 iterations, it ended with a taxi trunk filled up with TNT, parked directly in front of the facade. I presented the result. I told them, facade is blown away. This is what we always said. I said, but your airport too. Then they got white-faced and they said, okay, make the bomb smaller. But what is typical that the energy induced by this exploding material, if you want to resist that with stiffness, it takes you endless size of girders or beams or whatever. But if you say, okay, if there is a wave, a propagating wave of air pressure, just make the facade totally soft so that it steps away, so that it consumes and damps the energy and transfers it into heat or whatever, friction and then heat, is the right recipe. And then we did some bomb blast tests in Switzerland with the Swiss Army, and we did some in North Ireland and so on. The thing is absolutely robust. Some of them are even triple glazed, insulated, triple, whatever you want. This is, see, if the facade deflects, it typically deflects homogeneous. It does not deflect here 1 meter and here inward, outward, so it's moving homogeneously. And if you then anchor the glass panes on 4 points only onto the cable, there's no warping in the glass. So the piece of glass is translated half a meter into another position, but as long as no warping occurs, it doesn't interest the glass. So working with deformability is something which is very important, because it at the very end allows you elegancy, lightness, simplicity. And by the way, those facades are not expensive at all.
Let's do one. I have a problem with that.
Yeah, great.
Yeah, thanks again.
Yeah, thank you.